Hey guys, welcome to the Chapter 3 guided assignment. This is just a whole sampling of assignments to help us work through the concepts of this chapter. I know you know what guided assignments are by now, but you know, as I'd explain it anyway. Anyway, so let's just get to it. So the first one here is there's a severe shortage of critical care doctors and nurses, blah, 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 blah. Okay, so you guys can read all this. But in essence, what they're doing is they did a study of wait times in ICUs. Let's see. And so here's our list of data, the amount of time patients have to wait. So, all right, so we're going to click on the data file option here and open it up in Excel. And really the desktop version of Excel works way better. It has just some functions that the other one doesn't. Oops. There we go. So we've got all our data here, the wait times. And then it asks us to compute the mean waiting time for the 40 patients to 2 decimals. So in Excel, instead of using the word mean, the function is equals average. And then you just highlight the data you wanted to take the average of. So there it is. There's our mean. And it wants us to do it to 2 decimals. So I'm going to tell Excel I want all of my answer output in 2 decimals. Right, here's where you can adjust the number of decimals. Once the median wait time, so you will do equals median, an open parenthesis, highlight your data set, close the parenthesis, which I think you don't even have to really close it. It assumes you will, but I do anyway, because I'm used to it, I guess. And then the mode. And we're going to use equals mode.sngl. Find a single mode. Problem with that is if there's more than one mode, it doesn't always return it correctly. But for this data set, we're good. All right. So the mean or average waiting time is 43.83. The median wait time is 43. The mode is 42. Remember, the mode is the data point that occurs most often in the set. Then it wants us to do the first quartile and the third quartile. So it's quartile.exe. And then array means highlight the set or the data set, the numbers you want to look at, and then the quartile. So for the first quartile, I'm just going to put 1. So it'll look like this. Equals quartile.exe, the data set A2 through A41, and then 1 for the first quartile. And for the third quartile, it'll be quartile.exe. I'll highlight my data set, hit comma, and then hit 3 for the third quartile. So it should be 41 and 45.75. Check our work. And hooray, we got them all right. So let's move on to the second one. This one wants us, so it gives us a much smaller data set. So it's so much smaller that it doesn't let us export it. So we're going to have to type it in by hand. So I'm just going to open up a new tab here. And I'll type these in: 26, 21, 19, 32, 34, 28, and 25. So there's our data set 26, 25, 21, 19, 32. Okay. And it wants us to do the range, the interquartile range, the variance, standard deviation. Okay. So to find the range, the easiest way to find the range is to sort this data. And that's this little tool that says A to Z. And you can sort smallest to largest. So now you can see it's in order from the smallest number to the largest. And I can just say this equals the largest one minus the smallest one. And that will give me the range. So to find the interquartile range, that is the range between the first quartile and the third quartile. So what I do is I do the first quartile and then the third. And I use that same function I used in the last problem, equals quartile.exe. Highlight my data set, comma 1. That will give me the first quartile. And then I'll do equals quartile.exe. Highlight my data set, comma 3. And so my interquartile range then is just going to be the third quartile minus the first quartile. For variance, I can just say this equals VAR dot, and this tells us it's a sample, so dot S. If it were a population, we'd do dot P, and then you just highlight your data set. And that will give you the variance. And then finally, standard deviation, which is just denotated with S. Variance, you'll often see denotated with a S squared, okay? So the standard deviation is the square root of variance. We could do it that way, or we could do equals STDEV dot S for a sample size, for a sample. Highlight the numbers in the sample set. There we go. This wants our answers in 2 decimals. So I'm gonna use the little decrease decimal button here. And if the decimals are just 0, 0, you don't have to put them. Like Cengage will accept them, like this 15, 9 for our interquartile range, a variance of 25.64, and our standard deviation of 5.06. There we go. We got all of them. All right, let's take a look at number 3. So this one wants us to find our Z-score. For this, again, it's a small data set. I'm going to just create a new sheet and hand input the data set 10, 20, 12, 17, 16. So the Z-score is just telling us, so it'll find the mean for us. We'll actually have to find the mean. And the Z-score tells us how many standard deviations above or below the mean a given data point is. So this actually wants us to, so if you're never sure like what inputs you need to figure things out, you can do this. So the function to find the Z-score is called standardize. And when you do that, you see it's going to want X, which is the number, the observed value, okay? Then the mean, and then the standard deviation. And so since I don't have the mean or standard deviation, I know that I need to find that first. So I'm actually going to do that first. So I'm going to say this is the average. So there's our mean. And then this is the standard deviation. Again, it's a sample, so it's .s. All right, so now we're ready to use standardize. So to find the Z-score of 10, I'll do standardize equals standardize. where where X is the number I'm looking for, like 10. The mean is this mean we found right here. And the standard deviation is the standard deviation we found right there. So 10 is 1.25 standard deviations below the mean. We can input that same function over and over for each of these, or we can use Excel's fill function to fill the formula down. The problem is if we do that, we want it to fill where it pulls the X from. We want it to move down to each one, but we don't want it to move where it pulls the mean and standard deviation from. So if we want to make this as easy as possible, we can use the dollar signs on either side of the C for mean and on either side of the C for standard deviation. And now this is telling Excel, hey, when we fill, we want you to actually shift the one for X down and look at each of these numbers here. But we want you to look at this cell and don't shift this cell, and look at for the mean and look at this cell, C9, and don't shift when you're looking for standard deviation. Then we can grab the little nail here, just pull it down, and you'll see this one looked at E2 for the X value, and it looked at C8 for the mean value, and C9 for the standard deviation value. And if I look at this one, it'll look at E3 for the X value, but it'll still look at C8 and C9 and so forth. So there's our Z scores. And there we go, got them all right. All right, sorry about that. I had to pause while I went to my class. And so now we'll start on number 4, which is annual sales in millions of dollars for 21 pharmaceutical companies follow. Click on the data file logo to reference the data. So if we click on data file, we're going to download it. Open the file. All right. Okay, so here's all of our data. Wants us to provide a 5-number summary in millions of dollars. So a 5-number summary includes the smallest value, the first quartile. I'm just going to label that 1Q for first quartile, median, the third quartile, and the largest number. So the easiest way, honestly, to find the largest and the smallest numbers is just to sort this information. So using the sort button, and it will sort smallest to largest. So our smallest will just be the smallest, and our largest will just be the largest. Find the first quartile, we'll do equals quartile.exe. For array, we'll highlight the data set, and then 1 for the first quartile. Find our third quartile, equals quartile.exe. Highlight the data set, and 3 for the third quartile. And then for median, we can do equals median. Highlight the data set. Whoops. Here we go. There it is. So that gives us our 5-number summary. Smallest value is 608. First quartile is 1861. The median is 4019. Third quartile, 8356.5. And the largest is 14,138. So we could check if we want to. See, yep, that was right. So part B, it wants us to compute the lower and upper limits. And so I had to actually go read this in the book because I don't do this in real life all the time. And it defines the limit as 1.5 times the interquartile range. So to find the limit, the first thing I'm going to do is find the interquartile range, which is just the third quartile minus the first quartile. And so now the limit is 1.5 times the interquartile range. Then to find the lower limit, we are going to say it is the first quartile minus the limit. And the upper limit is going to be the third quartile plus the limit. So in essence, when they're looking for outliers, what they're looking for is anything that would fall outside of a range of 1.5 times the interquartile range. And then that range of that limit below the lower limit, I'm sorry, below the first quartile or above the second quartile or third quartile. That's going to give us our upper and lower limits. So anything that would be less than negative 7882.25 or more than 18,099.75, we would call those outliers. So then the question is, does your data contain any outliers? And the answer is no, there's nothing less than negative 7882 and nothing higher than 18,099. So no, the data does not contain outliers. D says Johnson & Johnson's sales are the largest on the list at 14,138 million or 14 billion, right? 14.138 billion. Suppose the data entry error had been made and the sales had been entered as 41,138. Would the method of detecting outliers in part C identify this problem and allow for the correction of the data entry error? So if someone had entered 41,138 instead of 14,138, that would fall way above this upper limit of 18,099. So the answer is yeah, if someone had accidentally put it in as 41,138, this method would help us recognize the error. So yes, a transposition would have produced an outlier and a review would have found it. We usually look for outliers so that we can figure out if they're an error or if there's something else going on. Part E, we're supposed to choose which box plot most accurately displays our data set. And so just knowing how to read a box plot helps. So the line in the middle is the median. And then the line on the top here is the third quartile, and on the bottom is the first quartile. And then these lines extend out to the range, as long as it's the range, not the range, but the highest and lowest value in the data set that is inside of the range. Okay, so I usually start with like the median and say, okay, the median of my data set was 4,019. So I'm going to look here, and this one shows the median somewhere between 5,000 and 10,000. So that one's not it. So I'm just using a process of elimination. This one shows the median also between 5,000 and 10,000. So that can't be it. This one shows the median just below 5,000. So that is going to fit with our median of 4,019. If I wanted to, I could also look at the first quartile here, down around just under the 2,000 mark. So 1861. and the third quartile under 10,000, just above the 8,000 mark. So this seems to fit. So I'm going to go ahead and select number 3. Check my work, and I'm good. All right, let's move on to number 5. So number 5 has ordered pairs, or 2 sets of data that are related to each other. Unfortunately, they're not, I can't just export it. So I'm gonna have to go speed at miles per gallon. My speed data is 29, 50. Whoops. And then my miles per gallon data, 29, 24. All right. Might make it easier for us to see if I can get all the data here on one page. I can adjust these by hand like this, or I could go and tell Excel some specific width to make them. And it's not necessary, really. It's just, all right. So we want to figure out the correlation coefficient, which tells us the relationship between these 2 samples. Just double checking my data to make sure I entered it correctly. It's pretty easy to make an error. All right. So the correlation coefficient, I can use a function called equals CORREL, and then array1, which just means the first data set, comma, array2. And that's going to return a correlation coefficient of negative 0.91426. So remember that correlation coefficient can be any number between -1 and +1. A -1 would mean a perfectly negatively correlated set of ordered pairs, meaning that for every time, negatively correlated means that every time like speed goes up, miles per gallon goes down, like perfectly. That would be a -1. So speed goes up by 3, miles per gallon goes down by 3. A +1 would be perfectly positively correlated, so that every time speed goes up, miles per gallon also goes up. So when we look at this and say a negative 0.91, we would say that's a negative correlation, and it's pretty strong. It's not perfect, it's not a -1, but it's a negative 0.91. So we'll put in our correlation coefficient, negative 0.91. Says, what can you conclude based on your computation? That there's a strong negative linear relationship between these 2 data sets. And then it asks us to interpret the correlation coefficient. And so our options are for driving speeds between 24 and 61 miles per hour. Higher speeds are associated with higher miles per gallon. That's not true because it's a negative correlation. Higher speeds are associated with lower miles per gallon. That's probably going to be our correct answer. Or lower speeds are associated with lower miles per gallon. No. Or there is no relationship between the 2. So we're going to say 2 for that higher speeds are associated with lower miles per gallon. Check our work. Looks like we got it all right. So we can move on to number 6. Here it says, consider the following data. And so it gives us values of X, and it gives us a weight. And again, we can't export it, so we'll just have to type it in. So in order to find a weighted average, we have to multiply the value of X times the weight. So I'm going to create a new column called X times W. And here I'm just going to calculate X times W. And so the formula for weighted mean is just to take the sum of X times W and divide it by the sum of W. So we're going to divide the sum of X times W by the total of the weights. So our weighted mean then will be the sum of X times W divided by the sum of W, or 3.695. Then it tells us to compute the sample mean of the 4 data values without weighting. So now we're not going to worry about the weights. We're just going to be, I'm going to call this the unweighted mean. So I'm just going to hit equals average and then just find the mean of these 4 numbers. So the difference between the two is pretty significant, right? It's like 0.52. And since our data set only has a range, the highest is 5 and the lowest is 3, we only have a range of 3, then a variance or a difference of 0.5 is pretty significant. It's 1/6 or about 18.5%. So that if we didn't use weighting, we would be off by 18.5%, which is pretty significant. We'll just check our work. Looks like we're good. And then we can move on to number 7, which again gives us a list of numbers. And again, we have to just type them in. (27, 25, 20, 15, 30, 34, 28, and 25. And now it wants us to compute the 20th percentile of each of these points, okay? So, or of this data set. So the best way to do this that I know of is to put in 0.2, 0.25. So 0.2 represents 20% or the 20th percentile. 0.25 is 25%, 0.65, and 0.75. So those are our percentiles. And then we can use equals percentile .exc. And to do that, we highlight the array using the data that it's looking at, and then the percentile value, that's what K is. And that will return the 20th percentile is 19. So we could type that in by hand for all of them. We could also use the fill tool, but if we use the fill tool, I'll show you, it's going to create issues because now instead of looking at this data set here and this percentile, it shifted everything down one. So that's actually going to throw us off. So instead, if we want to do that, we've got to use the little dollar signs to lock the array in place. So we're going to put a dollar sign on either side of the B and B2, and on either side of the B and B9 on mine. And now that's going to tell Excel, hey, when I fill down, lock this in place. So always look at this array, but adjust the percentile with the fill. So I do that, and then I can see that this did B2 through B9 as the array, but D4 as the percentile. This one, B2 to B9 is the array, but D5, and then D6. So there's my percentiles, 19. There we go. Check our work. And that's it. So hopefully that was helpful, and it will help you with the rest of the homework. And I hope you have a great day.